Hi guys, I'm Romel and my teammates are Avinav, Abhishek, and Karthik. Here we present semantic hierarchy emerges in deep generative representations for synthesis. Next. As we all know that GANs have been pretty successful in generating any kind of images given some kind of training distribution. However, the problem remains in quantifying the aspects of the GAN or the latent space itself that results in different features of the final image. Next. In this project, we re-implement the methods described in the paper, and we in the whole process itself we train our very own GAN and we experiment on the latent space itself to generate new kinds of images. Next. The original paper was based on Elson and Places dataset. However, we also extend the methodology to Celeba and CATS dataset. And in this whole process, we have also incorporated different kinds of image manipulation techniques that were featured in the original paper. Next.
So the approach we have taken to do this consists of three steps. First is creation of the GAN. Second one is the generation of the latent space boundaries. Third is the layer-wise concept ranking. Next. The generative adversarial network that we have used over here is the style GAN. This is quite interesting because this uses noise at every layer. This uses latent code at the beginning, which converges and forms a W vector. This W vector is used to define the variance and mean for the upsampled images using the ADAN algorithm. There is also noise being injected into every layer. Next.
So we use the latent space of a particular layer for all layers. That is, for a particular layer's latent space, we identify the regions with the absence or presence of a target concept with the help of a linear boundary, which is usually found by training an SVM. This is called probing of the latent space. As a result, in the latent space, moving in directions normal to the boundary leads to an increase or decreasing presence of the concept. Next. As we can see in the photo of the bedroom, for the particular target concept called lighting, moving in the direction of the normal increases the lighting. Here Fi is the score of the concept classifier and G is the generator which generates images by sampling from the latent space. Now to rank the manipulatability of concepts in the latent space of a layer, as can be seen in the formula shown on the slide, for a concept I, the perturbation score delta Si for k samples is defined as shown. For a particular layer, the concept with the highest perturbation score is the one which is most easily manipulatable without affecting other concepts. Next. For a particular layer, the concept with highest score is then chosen to be manipulated. So as can be seen in this diagram, layer 0 is most suited to changing the layout without disturbing other concepts, while layer 13, the last layer, is most suited to changing the color scheme without changing the other concepts. Next.
Now I'm going to discuss some results. And we carried out several experiments, and we used a lot of pre-existing classifiers to use the existing boundaries as well as create our own new boundaries, and then move along in the direction of those to see what kind of manipulation does it produce in the image, and does that manipulation make sense. So these are some of the results. For instance, you can see very clearly that how the color of the cats is changing, and in the bottom row, the cat goes from gray to straight on a completely black cat. So that's a very visually appealing result, and it sort of makes sense because the boundary which we used was indoor lighting, and as you increase the lighting, it appears as if someone took a picture of the cat with the flash on, and that sort of verifies the hypothesis of the experiment that the later layer contains the tertiary characteristics of an image. These are some more images which we again generate by just changing the lighting and moving towards the boundary of indoor lighting. Next, we experimented with the syllabi dataset and the faces, and we tried to move in the direction of changing eye colors, and we identified that the highest of the layers, they are able to produce a change in the eye color geared towards turning the eyes blue, and there is a stark contrast between the original and the final image. These results between the out of 11 layers are from the layers 6 to 11, and they were the boundary was generated using an age classifier, and you can clearly see that you can see that the person appears to getting younger with every image, and this is the final result. And if you contrast it, it's like pretty stark, and we were able to control this by moving in the direction of that particular boundary. And then we also verify that the lower layers, they sort of occupy a more they change the more basic of the features, like the actual features of the person or the structure of their face. And as we go towards the boundary, the face starts to change, and like towards the end, the hairstyle and the facial structure has changed completely. And there are many more results that we like experiments and that we carried out, but it's too hard to summarize them all in a video, and we will cover them extensively in the report. Thank you so much.